Can folks in the chat hear me? Wonderful, thanks. Okay, so as always, remember the seating survey, Chem 112, Section 003, ILC 118. Upcoming deadlines we have the today content video quizzes, 3 of them. There is, so the last one had initially had a mistake in it of only allowing you 1 attempt. I have fixed that, so if you had problems with that, you can go back in now and do it again if you so wish. Also, the small group activity quiz due today at 5 o'clock. Friday, a 3-part homework. Sunday is the usual cutoff for the participation points. And next week, exam number 2 is going to be released on Thursday and will be due the following Sunday. So, some important details. In case you aren't aware of it, on Thursday of last week, I went through an extended exam-style problem analyzing kinetic mechanisms. And so it is probably worthwhile to take a look at that to see the kinds of things that, that could be done with a kinetic mechanism in an exam-style question. This one has an overall reaction with 2 separate proposed mechanisms, and then we have a discussion of figuring out what the overall rate law would be for each of those mechanisms, and then how we could experimentally tell the difference between the 2 to determine which one's more plausible. There is a what we know so far post on Piazza about midterm exam number 2. I will keep updating that as more information becomes available. I have formula sheets up on Blackboard for both exam 1 and exam 2 now. The promised kinetic simulation spreadsheet is up on Blackboard along with a tutorial video on it on YouTube. This goes through both how to use Excel in general, because I have heard certainly from a number of students that they may not feel very comfortable with their Excel skills. So I'm taking you through the specific skills that will allow you to do the kinds of analyses that will be necessary for this kind of work, as well as the video takes you through the specific kinetics practice spreadsheet, simulation spreadsheet that I have posted, how to set up different kinds of problems to test yourself on, and then specifically how to take the simulated data, plot it versus time, plot the natural log of it versus time, plot 1 over the concentration versus time, so that you can see which reaction order it might be, to then extract the rate coefficients from it, how to use the method of initial rates, how to use the method of flooding in this spreadsheet. So I recommend taking a look at that and getting yourselves familiar with it before the exam next week. Do we have any logistical questions before we get started on some content? Okay, we will go straight into some content. All of the questions that had been posted are on the equilibrium material, so this week's set of material. And it looks like there is some general sort of confusion about how to construct reaction quotients and how to construct equilibrium constants in general. So instead of diving first into the specific questions that came up, I kind of want to just do a little bit of a reset and talk about how we understand equilibrium constants and reaction quotients, and then and so how we can construct them. So the basic idea is that if we have some kind of reaction stoichiometry, that's in equilibrium, like this, then the way we write an equilibrium constant is going to be very similar to how we would write a reaction rate law if these were elementary reactions. The key things to keep in mind that's different about the two is that you don't put the rate coefficient in it, and you create it as a ratio of the products over the reactants. So what we'd, if we were looking at the rate of the reverse reaction, it would be a R minus 1 is K minus 1, concentration of D to the D, concentration of E to the E, concentration of F to the F. So for our equilibrium constant, we do all of this without the K. So D to the D, E to the E, F to the F, over the same thing but the reactant side. A to the A, B to the B, C to the C. Okay. So this is the format that you do it in. You simply take the reaction stoichiometry, you use the stoichiometric coefficients as the powers, and you just multiply everything together, and it's reactants over products. Now, the KEQ, the equilibrium constant, is this ratio when the system has reached equilibrium. So I'm subscripting these with EQ for it being at equilibrium. The reaction quotient, Q, is the same expression, just not necessarily when it's reached equilibrium. So just that. So you can have the system not be at equilibrium yet, and Q is the same ratio of the concentrations that you would have in the same format as you would have for the equilibrium constant. It's just that this is actually a constant, and this is whatever your conditions are. So the way to think about what's going on here is that, if you look at, say, having a reactant, so if these are concentrations of things, and so you have a reactant and you have a product that are approaching equilibrium, and if this is time, so this would be something like A, and this would be something like D that we're looking at. At some point, you get to a point where the concentrations have reached equilibrium, and so at every point beyond that, this particular ratio of concentrations will be the same value as the equilibrium constant. At times before you reach equilibrium, then your ratio can be anything based on how you created the system in the first place, and that's what you have for the Q. Okay, that general idea making some sense? Okay, so the one modification we need to make to this is keeping track of which of these species we actually need to include. Certainly any solute, certainly any gas, but a solid or the solvent or a liquid by itself, those you do not include, because if you think about the concentration of a solid, for example, piece of paper here. You think about a solid, say sodium chloride solid. What is its concentration? Well, it's the number of moles of sodium chloride divided by the volume of the sodium chloride, not of whatever it's in of the sodium chloride solid block itself. Well, this is just based on its density in the molar mass. So this is a constant. It's a constant if it's for anything that's a solid or for anything that is a liquid. So what we do in that case, because we only want the equilibrium constant and the reaction quotient to have in them concentrations or partial pressures of the things that are changing or that matter. If, for example, C here was a solid, then we would take C and we would fold it into the equilibrium constant on the other side, so that our equilibrium expression here only contains solutes and gases. Okay. Any questions on how to construct one of these expressions for an equilibrium constant or a reaction quotient? Okay. So one of the first questions we have here is, what's the difference between Q and K? The fundamental difference is that K is after you have reached equilibrium, and Q is any time before you have reached equilibrium. The importance of the difference between the two is that by comparing the two, you can tell which direction the reaction is going to proceed in order to approach equilibrium. Okay. So if we look at the example I've drawn here, let me actually do a different color. Oops. Boy, that's a horribly drawn line. Okay. So if we've got A here in green and D in blue, over in this, at this point, we have more A than we will have at equilibrium. And we have less D than we would have at equilibrium. So if we look at the expressions, we have the Q we have is going to have a larger denominator and a smaller numerator, meaning that here, Q is less than K. Does that make some sense? Think of it as we have less products and more reactants than we would we expect to have at equilibrium. And so if we in fact have less products than at equilibrium and more reactants at equilibrium, then in moving toward equilibrium, the equilibrium is going to shift from left to right. The reaction is going to shift from left to right. So Q less than K means the reaction is going to shift to the right as it approaches equilibrium. The opposite is true when Q is greater than K. A Q greater than K means that the numerator is too big or the denominator is too small. Numerator too big means you have too much product. Denominator too small means you have too little reactant. And so to move towards equilibrium, you would be shifting the other direction from from products to reactants. Does that make some general sense? This is the essence of Le Chatelier's principle, the idea that you can predict which direction the reaction will shift based upon what you have too much of, what you have excess of. So if you have a system that's already at equilibrium, and then you add some product, then which direction is the reaction going to shift? Towards product or towards reactant? Yeah, towards reactant, exactly. So the system will shift in the direction that reduces the effect of the perturbation you've added. So you've added some product, so the reaction will shift away from product towards reactant. Okay. So that's the idea of the difference between Q and K. So the next question we had was kind of specific. For an equilibrium constant, does the solute always come first in the equation, or does it sometimes change Which substance, the solute or the solvent, do we keep in the concentration equation at the end? So this sounds to me like this is talking about a specific kind of equilibrium, which is the solubility equilibrium. So what we're going to talk about here is not about equilibria in general. It's about the specifics equilibrium for solubility. And so a solubility equilibrium would be something like NaCl solid is in equilibrium with Na plus aqueous plus Cl minus aqueous. Okay. And so let us write down our equilibrium concentration equation for this. Can anybody tell me how to start doing that? So the chat says put products on top. Okay, that's right. So our products are going to be Na plus, Cl minus. What powers do we put these to? 1, correct, because the stoichiometric coefficient of sodium and the stoichiometric coefficient of chloride are both 1. The chat also says put a 1 on the bottom because this is a solid, so it doesn't factor in, so just a 1. So our equilibrium constant is just concentration of sodium times concentration of chloride. Now, because this is a very common type of equilibrium to talk about, it has a special name. It's called the solubility product. And so we designate it with the SP. And so, yes, when we are looking at an equilibrium that is a solubility product, that designation solubility product means that we have the solute on the left. We have the undissolved solute on the left, and we have the dissolved solute on the right. So that's the convention by what we mean by solubility product. And so I think you can probably see that for a solubility product, whatever you have on the left is never going to factor into the equilibrium constant because it is always going to be a solid or a liquid that you're dealing with. And so you're simply going to have the product of all of the components that it dissolves into on the right, which is why this is called a solubility product. These are the things multiplied together. So the name makes a little bit of sense, which is always nice. It helps you remember things. So, so that is how this is structured. It is not generally true that the solute will always come first. It is just a function of it being a solubility product in this case. Which substances do we keep in the concentration equation at the end? You keep the ones that are dissolved or gases. That's the general rule. There's nothing special about this one that's any different. It's just that in this case, we know that the thing on the left will not be kept because it is a solid or a liquid. All right, any questions clarifying solubility products at the moment? We will have a later section, I think 2 or 3 weeks from now, that's going to be specifically on solubility products, so we're going to be coming back to this in more detail. Okay. Writing reaction quotients. Why are solids left out but gases aren't? It's the same thing for gases and, it's the same thing for solids and liquids, and it's the same thing for reaction quotients as it is for equilibrium constants. The reason is that solids have a constant concentration. You cannot change its concentration. It's just based on its density. Gases, you can change the concentration, moles per liter. And remember, if we take the ideal gas law, PV equals nRT, we can solve this for N over V, which is a concentration, moles per liter, molarity. And so in a gas, you can have different concentrations by simply changing the density of the gas, changing the partial pressure of the gas, which is what this is right here. So it is something that can change, and so we keep it part of the equilibrium constant and part of the reaction quotient. Okay. There was a specific question about a problem in the very first quiz question in the ICE tables video. I am confident this is impossible to read, so I will reproduce the information before we talk about the question on it. So in this particular quiz question, we're looking at the KSP of magnesium phosphate and this has a value of 1.04 times 10 to the negative 24th units of molar to the fifth. We had an ICE table that was set up, Mg3, PO4, 2, solid, equilibrium with 3 Mg2 plus, aqueous plus, I didn't leave myself enough room, 2 PO4, 3 minus, aqueous. We have our ICE table, initial, change, final. This doesn't matter over here. And we set this up by saying we made the solution saturated in magnesium fluoride, if I remember correctly, and that gave us a 0.00210 in units of molarity. And we also made it saturated in lithium phosphate, which gave us a 0.0544 molar phosphate ion concentration. And so then the question was, how do we use this information to know that the equilibrium is going to be shifting to the left instead of shifting to the right? And so what I had done in this was to put in, this is going to be minus 3x, this is going to be minus 2x in order to then determine our final line. And so how do we use this information to know that it's going to be going to the left? The place we get that information is looking at the solubility product value we have here. Notice that 1.04 times 10 to the negative 24 is stupidly small. It has 23 zeros after the decimal point before the 1. That means that in the final analysis, when we look at this set of concentrations at equilibrium, both this concentration and this concentration are going to have to be extremely tiny in order for the product of them to equal 1.04 times 10 to the negative 24th. Yes?
So I noticed that on your table you put the product side is negative and negative. When I was doing the Newton, sometimes the product would be negative and sometimes the reaction would be negative. So how do you know when?
Okay, so for the chat, the question is that she was noticing that in Newton, sometimes the products are negative, sometimes the reactants are negative. How do you know which way to go with that? And the answer is that you hopefully would be able to look at the equation, at the reaction, and your starting initial conditions, and get some kind of sense as to whether you are whether you're too far on the equilibrium to the right or too far on the equilibrium to the left. And that's exactly what I was going through right here, which is saying that at equilibrium, in this case, the solubility product here tells us that these concentrations have to be tiny. And so looking at these are small but not tiny. And so in order to get to equilibrium, the equilibrium is almost certainly going to shift from left to right, and so the concentrations will go down. Now, it is always possible to make a mistake about that sort of thing, and you put in you choose the wrong sign on your change line. If you do that, then what you will find is that when you go through the math afterwards and solve the equation, you'll find an x that is negative, that's pointing you in the other direction. And that's okay, that's perfectly fine. So if you choose the sign incorrectly, this is a self-correcting problem, because it will then, when you solve the algebra later and get your value for x, it will tell you it's a negative value, and therefore you made the wrong assumption earlier. And you don't have to go back and change it and redo the calculation. You just say, okay, x is negative, that's fine. And so when we come down to here, 0.00210 minus 3x, well, if x is negative, then it's going to be this value plus something, right? Negatives cancel, and that's fine. The one thing you have to do is to make sure that once you do that, that the resulting final concentration is not negative, because that's a non-physical concept. That is the piece of information that will tell you which of the possible solutions to the polynomial you come up with are the real ones. Okay, so does that help? Okay, so any further questions on, determining what to do on the change line? Okay, well, that was all of the muddiest points that I had. I am happy to talk about anything anybody here in class or in the chat has about any of this material. If there's stuff on equilibrium, we should probably do that first. After we get through some of the equilibrium stuff, if people would like me to, I can pull up, if there is Excel on this computer, I could try to pull up the spreadsheet for the kinetic stuff and talk through a little bit of how that's working. I see a nod about that, but let's do some equilibrium stuff first, and then we'll come to that, so that we're trying to keep concepts together. There's something from the chat. I was having trouble understanding the very last part of the ice table video where you made assumptions about the concentrations. Okay, that is a very good thing to talk about. What I'm going to do is switch to the PC, and I'm going to call up that video so that we can look at the same example we had. And I will share screen in a moment for the people in chat once I'm close to the right spot. Content videos, equilibrium, ice tables, do that one. I'm going to go to full screen. I'll switch to this in a minute. Let's go to here and share screen. All right, can the chat see this? Make sure. Yes, wonderful. Okay, so let's get over to this problem right here where we had that neglecting it. So I'm going to back up slightly to this and explain why we need to do it in the first place. Okay, why we need to go to the approximations stage in the first place. So the idea here is that in this particular example, when we go through the math, plug in minus x, minus 4x, and x here, and we look at the result that we get here, there are two problems we have. The first is that if we multiply this out, so this to the 4th power times this, we're going to end up with an x to the 5th that's part of this. We end up with a 5th order polynomial that would have to be solved. And so we've got the quadratic formula when it's squared, but 5th order is nasty. And so my recommendation, if you ever have to do that, is to go to Wolfram Alpha and just say, here, do the algebra for me. I don't even want to deal with it. So that is a nasty aspect of it, is that you're dealing with a polynomial that's pretty big. The second problem is if you actually do that and you go and see what Wolfram Alpha kicks out at you, you find an answer for x that is so ridiculously close to the the initial value of the copper 2+, that essentially that's saying there's going to be none left. And now if you want to know how much copper 2 there will actually be, do you trust these digits way down here at this point? I don't know. Probably not, because we don't have that many significant figures in what we're dealing with. So we need an alternate approach if we actually want to get an answer to how much copper 2+ there's going to be. So that alternate approach is to come over here and notice what we talked about a minute ago about looking at the magnitude of the equilibrium constant. The one we looked at a minute ago was stupidly small. This one is stupidly big, 10 to the 13th. We're talking about 50 trillion is the magnitude of this equilibrium constant. So if we have that huge an equilibrium constant, then that says that the numerator, which is the products, is going to be huge, and the denominator is going to be tiny. So what we should do then is adjust our initial conditions to say, let's just assume the whole thing reacts away. So we then subtract off all of the copper 2+. That means that because it's a 1-to-1 stoichiometric ratio between these two, that means that our resulting amount of this complex ion is going to be that same amount, 0.01. And we subtract off 4 times that amount of ammonia because there's a stoichiometric ratio of 1-to-4 here. At that point, we now know, or we now strongly suspect, that we're pretty close to equilibrium. It's not going to be right because there's going to be a little bit of copper 2+ here, but it's not going to be much. So this is going to be close. And that means that when we look at our next line, our change line, whatever x ends up being as it switches back slightly to the left is going to be very, very small. So if x is very, very small, then let's look at these expressions right here. If x is like 0.0001, that's past the digit that we have on the 0.96 here. And so as a result of that, that means that this part, the plus 4x part, is negligible. So we just drop it. Same thing here. If we've got 0.00001 in the x over here on the 0.01 under the copper nitrate, that one's also going to be negligible. So we strike them both out, and that makes our resulting equation, when we plug it in for our Kc expression here, much easier. The only place the x appears is right here in the Cu2+. This now is something that you don't need Wolfram Alpha for. You can do this in a normal calculator. You calculate it out. 2.4 times 10 to the negative 16 molar, which is absolutely freaking tiny. And that validates the assumption that we made that the 4x was small compared to the 0.96, and that the x was small compared to the 0.01. And so that means that our assumption was okay. All right. So, all right. We have a question, some questions from the chat. Will you always be given the initial values? I think so. If you're not given an initial value, then you'd have to put a variable up there. But then you'd have to be given some other piece of information somewhere. So, I mean, you can do that. You can put a variable up in the initial line if you want, but I don't see, but I can't think of a good example of where you'd want to do that. There was another question, which I just lost. How did I know the x's were going to be so small? So we know that it's going to be, the first thing you do is you assume that they're going to be small in order to simplify the equation. And then you check your answer afterwards to see if you're right. Because the idea is, let's make our lives easier, do the math, and do the easy math. And then if the math shows us that that was okay, great. And if it shows us that it's not, then you go back and do the hard problem. The second reason is that when we look at the equilibrium constant itself at 5 times 10 to the 13, that tells us that the true equilibrium position is going to be very, very close to everything being on the product side, because the numerator has to be huge, the denominator has to be tiny. So it's a question of looking at the equilibrium constant itself to figure out where you think the equilibrium is going to be. Do a shift of your initial conditions so that you're starting as close to equilibrium as you think you can, and then try out, is the assumption going to be okay or not? So if you've got something that's 10 to the large positive number, shift everything to the product side. If you've got 10 to the very large negative number, then shift everything to the reactant side, and you start from there. If you've got something that's an equilibrium constant of 100, that's neither one, and so you're not going to be able to make an assumption that it's all one way or all the other, and so you'll whatever the resulting equation is you get, you're going to have to solve in its full glory, unfortunately. So you said, so we'd make this guess if the math is too complicated the other way. Yeah, absolutely, yes. And then said we'd take 4 times the number to get 0.96 because of the stoichiometry of ammonia, but I don't see what 4x is for. Okay, so the idea is we're starting with 1.00, and we are removing 0.01 of the copper, which means we're removing 4 times 0.01 of the ammonia because of the stoichiometry. Because there's, for every copper ion that gets used up, there are 4 ammonia molecules that get used up. So 4 times 0.01 is 0.04. We subtract 0.04 from 1 to get 0.96. Does that help? You're welcome. Okay, so was that a sufficient explanation for the folks in the chat? Oh, I'm sorry, the question here, yes.
So if the reactants are decreasing, how come the X is positive?
So, okay, so the reactants are decreasing relative to the initial line, but the shifted initial line, the reactant is 0. So it's going to be from the shifted initial line, it's going to be shifting to the left because you have to have something there. Does that help? Okay. All right, so did this sufficiently answer the question from the chat about what's going on with these approximations? Okay. All right, let me switch this back. All right, what else can we talk about? Is there anything else on equilibrium? Somebody in the chat is saying, Yes, it answers it, although it would be nice to have some practice. Sure. So I think that you're going to find that there's going to be a lot of practice of this within Newton. So, I mean, one thing you could do very easily is go to look up solubility products for ionic compounds, and you'll be able to look up that magnesium fluoride has a solubility product of some number, and I don't know what that number is, but you write out that number, and then you take MgF2 solid, and you practice writing what the dissolution reaction would be. You should definitely know how to do this. And then make up some starting values that you have. Put them in. So, and then see what's involved in solving the problems. And what I would recommend is, if you do this, when you find a table of the solubility products, which are easy to find on the internet, you're going to find some cases where the ionic compound is a 1-to-1 ratio. So, sodium chloride is a great example of that. So in that case, the coefficients are easy. Then you start working your way up to a case where, well, one of them isn't 1. So you've got a magnesium fluoride where it's 2 fluorides right here. You have to deal with that. Then you work up to examples like the one I just showed you, where one of the ions there were 3 of, and the other ion there were 2 of. And so you now have a more complicated situation to work through. And so more than almost any other example type in chemistry, this is an example problem type that it's actually very easy for you to make up your own problems to solve. So, okay, anything else on equilibrium at the moment? Or would you like me to see if I can pull up this kinetic spreadsheet and we can talk through some of that? I see a few people would like the kinetic spreadsheet. So let me first make sure that this computer has Excel. It does. All right, excellent. Switch to PC. So if we come in Blackboard, did I start? I didn't start screen sharing, did I? Let me do that. Here we go. So if we come into Blackboard and we go into exams, there's now a folder for midterm exam 2. And there's a link here to the formula sheets that I have put together for you. There's a link here to the practice kinetic simulator spreadsheet and to my YouTube channel where I have the tutorial for using it. The tutorial is going to have much more detail about how to handle things than what I'm going to go into right now. Definitely worthwhile looking at it. Even if you think that you are confident in your Excel skills, there are some quick little tricks that I mention in there that will let you, if you have like 500 data points, that will let you get to the end of that list very quickly so that you can select the range in order to either do a calculation on all of them simultaneously or plot them all, something like that. So I'm going to go ahead and download this. I don't know where it's putting it, but that's okay. We'll open it. And this is apparently not a really fast computer. Here we go. Okay. So what we have here is a workbook that has 3 sheets in it. So the experiment setup sheet here is the main one we're looking at. Well, it has to reopen it apparently if I say enable editing. There we go. All right. So the experiment setup sheet that we have here, a rate law sheet that lets you define what the reaction and the rate law is that you're going to be looking at. And then this thing called Runge-Kutta, which you don't need to ever look at. The Runge-Kutta one is the one that does all the stuff behind the scenes to do the simulation for you. And if you don't go try to do anything with that, because it's A, it's confusing, and B, if you change anything over here, it's going to screw up what's going on the other ones. So for the exam, you will only have access to something like this front sheet. For this practice spreadsheet, you have access to the middle one, so you can change which reaction you want to look at. So the general design philosophy of these sheets is that the only things you should change are the things that are in yellow. So you can change the temperature, you can change initial concentrations, you can change which species you're monitoring, and you can change the time information that you're taking data. So you're taking data for 500 seconds every 1 second. So that's what's currently set up right here for this. So those are the things that you can change here on this sheet. On the rate law screen, we can change the rate law by changing things in the reaction order column. We can change the reaction stoichiometry by changing things in this column. I'll talk about that in a second. We can change the rate constant, the rate coefficient, by changing its frequency factor and its activation energy, so that you can, and then the calculated rate constant is here based on the temperature that we set over here. And then there's this thing called noise level, because when you take experimental data, no measurement is exactly precise. And so this specifies how much noise there is. So in this example here, if we have 1 molar initial concentration, you can't really see the noise very much. But if we start with 0.1, hello, why is it not updating? Formula. It's on manual. I'm going to have to change that. Okay, I've now changed it to automatic updating. So if anybody's tried to do this, that's a problem. I will fix it and I will re-upload. So if I set that to 0.1 instead of 1, we see now that there's some noise in the data. If we went to 0.01, we would see that there's a lot of noise in the data. So if we want to be doing something at lower concentrations, then we could say, okay, maybe we have a more precise instrument and we don't have nearly that much noise, and we can come back over here. So in the exam version of this, where you're not able to go over to the rate law, I'm going to have the noise level set to something that is going to be reasonable for the calculations you're going to be doing. But for your practice, you may need to, you may want to play with it to get it to a point where it has some noticeable noise, but not enough that it's going to interfere with the calculations you're doing. Okay, so the way that this system works is that we have 6 possible species that could be either reactants, products, or catalysts. We have, and we specify the stoichiometry over here, where we use the stoichiometric coefficient, and then if it's a reactant, we make it negative. So if we wanted, say, 2A plus B yields C plus 2D, we would do that. And you can look down here and see that it is, see that you did it correctly. Okay. You can set up reaction orders here as well. So right now it's set up as a simple first order. I'm going to switch this back to just A goes to B in order to have a simpler system. You can change this to 2 to make it second order, in which case we come back over here and let me go to something a little higher than that. And we see that we get a slightly different shape that we have. And you can change things about the rate constants as well. If you put something in here for a species that's neither a reactant or a product, that is now a catalyst. That's going to be part of the reaction. The one thing is, do not put reaction orders for products. The reason for this is that if you think about time zero, the very minute that you create your sample, your concentration of products is 0. And so if you put a reaction order on the products at this point, you will end up with everything being multiplied by 0 to some power, and so your rate becomes 0, and so the reaction never happens. So while yes, there are rate laws that have the products in the rate law, it being in the rate law is an approximation because of a mechanism that is going on, not because it's fundamentally part of it. And and so when we go through something like the steady state approximation or the pre-equilibrium approximation in order to get the overall rate law where we end up with a product in it, that is making an assumption that doesn't work at time 0 exactly. So we're not going to be doing anything here with a product in the rate law. Okay, there's a question in the chat. The Excel spreadsheet for the exam will be given to us. Yes, the Excel spreadsheet for the exam will be given to you. It will be very similar to this one. I may even release it to you before the exam actually starts. I'm not positive about that yet. I'm still working on writing the exam. So we will see about that. All right. So, so right now what we have is an example reaction that is currently listed as simple first order. And in the tutorial video, I talk you through how to take this data, put it into your own spreadsheet, and then do an analysis of it. So I'm going to look very briefly at a way to do that. So if we want to analyze the data we currently have, you can click up here and type in capital X, comma, capital Y. I've set up named ranges for the time and for the concentration that I've called X and Y. You hit enter, and it has that now selected. We can Control C to copy it, create a new blank workbook, and we can Control V to paste. And actually, I shouldn't have done it that way. I'm going to do a right click and paste values because we don't want all of the formulas coming over. We just want the numbers coming over. Okay. And so this is time. This is concentration. If we want to see what kind of reaction order it is, we're going to want a column that's going to be natural log of concentration, and we would want one that's going to be 1 over concentration so that we can test each of the possibilities. And I go through how to do all of this in the tutorial. So if we put a cursor here, we can say equals natural log of this cell. Those parentheses hit enter. It takes the natural log of it. And we can now take that, use some of the tricks that I talk about in the tutorial video to copy that formula over the entire range that you have here. We can now select this entire range, and again, oops, okay. Back up here. We can insert a chart, a scatter plot, and that looks pretty nicely straight, doesn't it? So the fact that we found a nice straight line for the natural log column means that this is first order, which you may remember back over here, that's exactly what we set right here. So we have confirmed that we have analyzed this correctly. Then we can add a trend line, which unfortunately shows up in the same color as the data points, so you can't see it. But what we can do now is, okay, get rid of that first of all. We can change the trend line so it's visible. Okay, and so it looks like a nice straight line. We can also come over here and display the equation for the trend line on the chart. We can change how many decimal places we see in the equation, and we see that we now have a slope of negative 0.00918. And so for the first order case, the negative slope is the rate constant. So let's see how close we are, 0.00918. Come back over here, 0.0091779. Pretty darn good. So I know that I went through those steps here in front of you very quickly. In the tutorial video, I talk through every keystroke, every click, so that you can see what these steps are to do the things that I've just done here. Okay. I also go through, okay, how do you set up the experiments so that you would be able to do the method of initial rates? How would you set up these experiments so that you could use the method of flooding? Those kinds of things. So, any questions on this? One of the things that might be, once you get sort of used to taking the data and analyzing it and extracting a rate constant, something like that, one thing you could do is find a partner, a friend, and have them set up the rate law for you. And then you do one for them, exchange spreadsheets, don't look at the rate law page, and then see if you can figure out, solve their puzzle, see if you can figure out the rate law that they came up with. So, you know, first order in one reactant, half order in another you could even do if you wanted to, second order in something else, some kind of order in a catalyst, something like that. And then see, and then pose that as a puzzle to your partner. And that would be really good practice for the kinds of things you'll see on the exam. Anything I can clarify? Any question about anything? Meaning of life? Yes?
So, for the reaction to argument that the leaching mechanism made it younger than it actually was.
Okay. So the leaching yes. So the question was, in the small group activity, her group came to the conclusion that the leaching mechanism would make the rock appear younger than it actually was. And yes, that is correct. So, so the idea is that when you get one of those measurements from the zircon crystals, whatever number you get out of it is the youngest that the rock could possibly be. It could be older than that. And usually there are other hints that we didn't go into in this particular activity that would suggest to you that there is an error, that there is an error that would cause leaching. But at a very minimum, it has to be at least as old as what that number was. Question in the chat, is the test cumulative or is it only the stuff we've learned the last few weeks? So the thing with chemistry is that the chemistry concepts are cumulative. So you're using dimensional analysis right now. You're using writing empirical and molecular formulas right now. It is unlikely that I would be asking you a question on this exam that would be focusing on, say, intermolecular forces. But that doesn't mean it's okay to just forget about them at this point, because there are plenty of upcoming topics where you need to understand that to be able to understand the next topics that are coming in. So, so I'm not going to be asking specific questions to test, do you remember stuff from exam 1? But it is assumed that that the exam 1 material is a foundation that you're building on for the exam 2 material. We have about 5 minutes left, if anybody has anything else. What kinds of questions will be asked about the Excel sheet? So you will get the Excel sheet, and you will be probably not just flat out. There will probably be sort of leading up questions to help guide you in the right direction, but there will be questions that will lead you up to what is the rate law for this reaction. I may say, using the method of initial rates, what do you determine the reaction order of this of the system in this particular component would be? Things like that. And then where that would lead to after determining the rate law would be probably something like the question from Thursday of last week that we did here in class, where once you have a rate law, you can then start to compare that against potential mechanisms. And that would then, so then I would give you a couple of different possible mechanisms for the overall reaction and have you derive what the overall rate law would be, and then have you analyze which of those mechanisms is consistent with the rate law that you experimentally determined through using the simulations in the spreadsheet. So that's the kind of thing that I would do. I could also ask you about activation energies, since there's a temperature component in this spreadsheet. You could be doing an Arrhenius plot to find activation energies and to figure out, and maybe use that to help distinguish between the different reactions or reaction mechanisms. So the spreadsheet is basically a tool you're going to be using to try to solve a problem. The reason for this is really twofold. When you look at how things like the Newton questions handle kinetics, you probably only get you probably only get like 4 or 5 data points or something like that, which is not how scientists actually do this. They do it more like what I showed in the spreadsheet, where you have 500 data points in a single in a single kinetic run. And so being able to see what are the tools that we use to actually analyze this, that kind of data is more useful than the sort of abstracted version where you only have 4 or 5 data points. Secondly, doing it the way I'm describing it, for where you actually choose what concentrations you're going to use, that gets at making decisions about what experiment is important. So if you're doing a method of flooding calculation, do you only do 2 data points for the 2 different concentrations and then see what kind of straight line you get? Or do you do 5 concentrations to make sure that it's linear? Because if it's not linear, then you might end up with a curve you need to deal with. And so making those kinds of decisions is the kind of thought process you need to be going through as you're thinking about the information. That gets at identifying what aspects are important about the information. So somebody's asking here, will the test be different from the last one? I mentioned making changes to them in response to the grades on the last one. So there are several changes I'm implementing. One of them is that I am trying very hard to give you more examples beforehand of what kinds of questions are going to be on the exam. So giving you this spreadsheet and talking through the kinds of things that are in it, I hope is prepping you better than you were prepped for the first exam. The second thing I'm making a change to is I am intending very strongly intending to ensure that this exam is shorter than the first one was, because I know people were feeling a lot of time pressure on getting the first one done. The third thing that I'm doing in response is I'm taking all of the feedback that I got and using that to help me in designing the wording of the questions that is being asked to try to minimize the leaps of understanding that you guys thought were there that I didn't see as leaps. And so I'm trying to use that information to help modify the wording of what's going on, of the questions. I also really want to emphasize that when you are taking the test over the weekend that this is happening, or the few days that this is happening, I'm going to be monitoring Piazza pretty much as constantly as I can. And I'm going to probably also be doing like I did last time, where I'm going to have large swaths of the day on Friday, Saturday, maybe even Sunday as well, where I'm going to try to be in my office hours. And so if something just doesn't make any sense, come ask me, either in Piazza or in the office hours and the extended office hours. I'm more than happy to, the worst I'll do is say, oh, you ought to know that. But more than likely, because my goal is for you to learn, it's not for you to get smacked down. My goal is for you to learn. I'm more than likely going to be trying to guide you through figuring out what's being asked for. So that's what I'm here for. All right, we are at time. Thank you all. And yeah, thanks.